Apple has initiated its next silicon cycle, and the immediate industry reaction has fixed on a single metric: the heavily marketed gains in AI compute. But those compute percentages obscure the physical realities of the hardware actually shipping. The utility of these machines is governed by the strict constraints of the two new hardware endpoints: the consumer desktop and the high-end workstation. Specifically, we are looking at two hard boundaries. The first is the 32GB memory limit on the new Mac Mini. The second is the 512GB memory ceiling on the top-end Mac Studio. Apple has now fixed a local inference capacity for the next year at these two precise numbers. The available RAM, not the speed of the processor, decides exactly which AI models can successfully load on either machine. To properly evaluate this hardware generation, we have to look past the advertised peak AI compute claims and strictly analyze the physical limits of memory capacity and bandwidth. Let's start with the M6 chip. The updated architecture includes a 12-core CPU complex and a 12-core GPU. Apple pairs this with a specific claim: a nearly 30% increase in peak GPU compute compared to the previous M5 generation. To understand why that compute figure drops out, we must look at how a large language model generates text, a process known as the decode loop. Generating a single token requires reading the entire model weight set from memory across a narrow bottleneck. Memory bandwidth reaches its limit long before all GPU cores can be utilized, leaving excess compute waiting on data. However, for context prefill, the GPU hits maximum capacity. This provides a genuine speedup for agentic workloads, parsing long tool call transcripts, ingesting massive system prompts, and processing data through vision encoders. But once the prompt is processed, the math reverts. For actual chat speed token generation from a large model, that 30% compute increase changes nothing. We can apply that math directly to the M6 Mac Mini, which is the machine most developers will actually put on a desk. This configuration operates under two hard metrics: a maximum of 32GB of total memory and up to 170GB per second of memory bandwidth. Here's the calculation. If you load a model occupying 24GB, you divide the 170GB per second of bandwidth by that footprint. The generation speed tops out at a hard ceiling of roughly 7 tokens per second. Reaching that 7 token per second ceiling assumes the model actually fits into the remaining memory budget. That budget includes a variable called the KV cache. While the model weights are a static size, the memory required to track the conversation grows dynamically with the length of your context window. Out of that strict 32GB, you have to budget for the operating system, the static model weights, and that constantly expanding KV cache. The 32GB limit acts as a strict cliff, not a gradual slope of degrading performance. If your context window pushes the total memory requirement to 32.1GB, the system does not slow down. It simply refuses to load the model. Stepping up to the workstation, the M5 Ultra inside the new Mac Studio presents a very different set of constraints. Typically, assembling hundreds of gigabytes of working memory requires clustering multiple discrete accelerators together. That means relying on tensor or pipeline parallelism, building interconnects, and executing a sharding strategy to split the model across different cards. The M5 Ultra bypasses all of that complexity. It offers high capacity while functioning entirely as a single address space node. The architecture achieves this using the Ultra Fusion interconnect. It physically bridges two dual-die chips to form a single quad-die array. The inter-die bandwidth across that connection exceeds 4.4 terabytes per second, allowing the hardware to present as one single memory pool. But that design point carries a trade-off. It provides massive, seamless capacity, but it sacrifices the extreme bandwidth per gigabyte ratios you get from stacked high-bandwidth memory on dedicated server GPUs. For the absolute maximum configuration of 512GB, Apple provides a total memory bandwidth of 1.2 terabytes per second. This calculation divides the stated 1.2 terabytes per second of bandwidth by a dense model filling the full 512GB memory. Before calculating any system overhead, the generation speed ceiling is roughly 2.3 tokens per second. If you only fill half that memory, using 256GB, the math dictates you get twice that speed. The capacity to bandwidth ratio is fixed. Apple has succeeded in putting an unprecedented amount of uncharted capacity on a desk. But doing so binds the generation speeds to a strict mathematical ceiling that no amount of GPU cores can overcome. We also need to contextualize that 512 gigabyte limit against the current reality of frontier open weights models. Loading a fully unquantized state-of-the-art model, like Qwen 3.8 Max, requires 4.8 terabytes of memory footprint. This scale comparison maps the 4.8 terabytes required by a true frontier model against Apple's absolute maximum offering of 512 gigabytes. This physical gap is why Apple's press release carefully promises the ability to run models with, quote, hundreds of billions of parameters. While Apple has significantly raised the ceiling for local inference, the hardware remains roughly an order of magnitude too small to host trillion-parameter models, boxing these machines permanently into an intermediate weight class. To evaluate hardware launches accurately, you have to look past the claims on the page and scrutinize what the manufacturer omitted. In this press release, there is a complete absence of absolute AI compute figures. There are no published tops, no teraflops, and no performance comparisons to any non-Apple product. Every metric is measured against an older Apple chip, like comparing the M6 to the M1 from 2020. This makes the claims unfalsifiable from the outside and impossible to cross-reference against the actual competitor hardware these machines are evaluated against in the real world. Furthermore, the phrasing relies heavily on the word peak. A metric like peak GPU compute is an architectural theoretical ceiling, not a measurement of sustained throughput on a real workload. The sharpest discrepancy is buried in the testing footnotes. Notice the hardware configuration used to validate Apple's claims. The heavily advertised flagship machine with 512 gigabytes of memory is not the machine that produced any of the published performance numbers. The benchmarked unit contained only half that capacity. Ultimately, there is only one benchmark that matters moving forward: an independent decode throughput test on a 512 gigabyte M5 Ultra, running a named open weights model at a specific quantization, measured in tokens per second. Until that specific third-party test confirms the hardware can reach its bandwidth-derived ceiling, the 512 gigabyte figure is just expensive shelf space rather than proven working capacity.